So it's my great pleasure to welcome Subarna to our MiDAS seminar this week. So Subarna is a postdoc at Harvard working with Stratos at DAS Lab. And prior to that, she was a postdoc in France at MiDAS team in INRIA in Rennes. She completed her PhD in the IIT Kharagpur. Maybe I'm not saying it absolutely correctly.
No, that's okay. That's
okay. And now she's working on SQL storage engines. And today we're going to find out more about how to make decisions about optimizing the cloud, so the cost on the cloud for NoSQL storage engines. So without further ado, Subarna, the floor is yours.
Okay, great. Thanks, Manos, for the introduction, and thanks everyone for having me here. And of course, thanks to Papun for always keeping me updated with what I need to do. So I'm actually happy to be here, not just because this is a platform for me to share my work, but it's also good that I'm seeing a lot of faces that helps me feel that I'm alive. Okay, so I'm going to talk about Cosine, a cloud cost optimized NoSQL storage engine. This is an ongoing work that I'm doing with the other members of my lab, Wilson Chin, Meena Jagadisan, Aaron Capsonel, and my advisor, Stratos Itriels. So today I'm going to focus on the question that if you have a budget to run an application on cloud, then how can you make sure that you fully utilize the budget and you kind of maximize the performance for running that application? And we're going to talk about all of this in the context of NoSQL storage engines. Okay, so let's begin. So NoSQL key value stores are used for a wide range of applications. Say the social media application, the graph processing applications, the event log processing applications, and there are many more. And these applications are backed up by the key value storage engines that we know of today. So some popular examples are RocksDB, MongoDB, Cassandra, HBase, and so on. Now, since the last few years, we've been observing this trend of migrating key value stores on cloud. And that's mainly because of two reasons. Firstly, cloud infrastructure offers this support of dynamic scaling up and down of resources based on the workload fluctuations. And this is a liberating thing for an application because they do not need to worry about these fluctuations ahead of time. And the second benefit is that cloud provides cost benefits as opposed to just buying and maintaining on-premise resources for storage and computation. So it's like at the end of the day, you just pay for only the resources that you've consumed, which is significantly cost effective. Okay, so now while this migration seems to be quite beneficial and promising, but we now have a new problem because of this. So now we cannot really reason about the cost that we pay for using the cloud services. So for a given cost, we wouldn't know what's the best performance to expect. Now let's take an example. Let's say you have a workload to run on cloud and you have say $1,000 to run it on cloud. So you got in touch with a couple of cloud providers and you said that, okay, see, here's my problem. And then one of them gave you one of the nicest deals, which is that, okay, you give me your workload and $1,000 and I'm going to run the workload in 3 hours. Well, how am I supposed to react to this deal? So I wouldn't even know if this is a fair deal or not, right? And this is also true for the counterpart. Like given a performance, I wouldn't know I have no idea what's the minimum cost to achieve that performance. So basically we can say that we don't have the knowledge to understand or reason about the cost performance trade-off on cloud. And that's normal because cloud systems are inherently complex in nature. So there are, multiple components within cloud systems. They kind of interact. They have a lot of interrelationship, which affects this trade-off. But the problem is that if we do not know how this trade-off looks like, we will end up paying more cost for a given performance, or we will end up getting a suboptimal performance for a given cost. So, it's as bad as, going to the market to buy something the price of which you do not know. And so you can easily get fooled by, getting a compromised quality or, paying really high price. But there's a good news. The good news is that cloud users themselves are in charge of this trade-off, and they can manipulate this trade-off exactly the way they want. So when an application is deployed on cloud for the first time, a cloud user needs to make 3 decisions. So the first decision is, who would be the cloud provider for this application? Okay, now this is a critical decision to take, because there are many cloud providers out in the market, and it is not straightforward to just compare them, because each of them has their own pricing policies. In fact, statistically speaking, it has been found that about 77% of cloud providers cloud users face this problem of picking the right cloud provider for them. And what is worse is that if you make a mistake here, say you thought that you're going to go with Amazon Web Services, and then after 2 years you found that that was a wrong choice, then the cost of switching providers can be so high that you are eventually locked in with that vendor. And then like about 57% of cloud users again face this problem of vendor lock-in, right? So this is one of the critical decisions that we have to take firstly. The second is, how much of hardware should that application use? And this has 2 parts. So how much of total hardware would go for that application, and how do we really distribute this hardware across the different virtual machines in cloud? And the third decision is, what would be the storage engine for that application? Now, different storage engines have different data structures beneath them, which actually control performance. So for example, if a storage engine is read optimized, it has a B-tree variant inside it. Or say if it is write optimized, then it has an LSM-tree variant inside it. What we do today is that we pick from off-the-shelf storage engines. Now, these storage engines are meant or designed for very specific workload types. So just picking any storage engine for any workload is likely to be suboptimal. And then once all of these 3 decisions are made, these 3 things, they start coming together and they start interacting and start affecting the cost performance trade-off in a non-trivial manner, and something that we cannot really reason about. So all the decisions that I've talked about today are kind of taken manually. So you can think that given the complexity and the size of this design space, firstly, it's kind of hard and time consuming to make all of these decisions. And secondly, it's impossible to get all of this right at the same time, right? Like you choose the best provider, the best design, the best hardware. It's impossible to have all of them right. Okay, so now that we understand the problem, what's the ideal thing we want to have? An ideal thing would be to have an oracle, such that if we just feed in a workload and a budget to that oracle, it's going to do some sort of computation and it's going to come up with the best answers to each of these decisions. Okay, so as a solution, what we propose is Cosine, which is that oracle where we feed in a workload and budget to Cosine. And somehow Cosine navigates through all the possible combinations of data structure, hardware, or cloud provider, and somehow it comes up with the optimal configuration. So by optimal configuration, what I mean is the combination of data structures, hardware, and cloud that optimizes this cloud cost performance trade-off on cloud. So in order to explain the internals of Cosine and to understand more about it, I'm going to divide the rest of my talk into 4 different stages. So firstly, I'm going to start with the 2 most important bubbles, the cost and performance, and I'm going to explain a high-level relationship of cost and performance. In the second stage, I'm going to bring in storage engine designs, and I'm going to say where this fits into the pipeline and how it starts affecting performance. In the third stage, we're going to look at how we can build hardware space if we have a budget or a cost as input. And in the fourth stage, we're going to use the demo of Cosine to look at end-to-end examples where we're going to feed the workload and budget to Cosine, and then we'll see what kind of configuration it generates, right? Okay, so let's begin with the first objective, where we will see a high-level relationship of how cost and performance are mapped together within Cosine. Okay. So do we have any questions so far before I started the mapping? I think Manas, you're muted, but I'm.
No, you said it's okay. You can continue. Yeah.
Okay, cool. So with a certain budget, or you can think about it as cost, what you can do is you can buy resources. Okay, and these resources can be of two types. It can be either a storage resource, so it can be like SSDs or HDDs, or it can be compute resource in the form of virtual machines. In cloud, virtual machines have different capacities. They can have different memory capacity, they can have different processing power, the amount of throughput that they allow can be different. And so depending on the capacity of a virtual machine, we can actually build the design space of storage engines within the virtual machine. Okay, I'm going to explain what I mean more about this in the subsequent slides. But for now, you can think about it as figuring out all the possibilities of different storage engines that we can deploy in a virtual machine. And once we have that, for all the different virtual machines that we've bought, for each such combination of a storage engine selection, we can get a series of performance. Now, note that all of these performance values really come from the same budget or the same cost. So it's like a one-to-many mapping for the cost and performance. Now, each of the components that I have mentioned here can have its own set of enumerations. So for example, cost can be a range of values. There can be different cloud providers. So for example, in Cosine, we've integrated it with 3 providers: Amazon Web Services, Google Cloud Platform, and Microsoft Azure. Of course, there can be different storage types, like I've said. The virtual machines can be different. They can have different configurations. Within a virtual machine, the storage engine design space that we create can have its own set of knobs with a different set of values. And all of these enumeration, when they come together, they create this 3-dimensional search space of designs, cost, and performance, where if you just keep one of these 3 things fixed, and if you just change the other 2, then you get a hyperplane of different combinations of the other 2. You can think about it as a trilateral trade-off of designs, cost, and performance. Now, as we try to get an understanding of how big the search space is, or what is the cardinality of the search space, we observe that the cardinality is really high, and it goes to something as high or even higher than 10 to the 35. What's interesting is that out of this entire search space cardinality, about 60% really comes from all the different storage engine designs that we can have. So storage engine designs is a dominant factor that really affects the cost performance trade-off. Okay, so now that we understand the high-level mapping of the cost-performance trade-off, and we do understand that storage engine designs are a dominant factor in the trade-off, we will see how storage engine designs really affect performance and how all of this fits into the pipeline. Okay, so this is a high-level structural, this is a high-level overview of how a storage engine structure looks like. So at the bottom, we have the base data, which can be laid out differently. It can be in arrays or logs or, trees, could be anything. And on top of the base data, we have an index structure, which allows faster access to the data. Now, the data and the index together make up the data structure design of the storage engine. And we'll also, call it designs or data structure designs interchangeably in the presentation. Now, there are different data structure designs that are used within contemporary key value stores. For example, say LSM-trees or B-trees or B-epsilon-trees, or log-structured hash tables. And each of these designs has their own set of advantages and disadvantages. So for example, say, LSM-trees are write optimized, but they do not facilitate good scans. Or say, B-trees come with read optimization, but they do have a write overhead. Or say, the log structured hash tables, they really support a good balance of reads and writes, but they do need a very high memory budget to do that. So the idea is that there is no perfect design that we can use globally for any workload. Instead, all of these designs are meant to serve very specific workload types. So given a workload, it's not just about picking the right design, but it's also about synthesizing the best design, which is specifically tailored for that workload type. So, how are we going to do this? So towards this, a first step has been already taken by a prior work, which is also one of the previous work from the lab that proposes design continuum. So I'm going to cover a bit of background here quickly. Design continuum is the unification of data structure design spaces. So the idea is that a data structure is nothing but a collection of, fine-grained primitives that control the data access patterns and the layout of the data structure. So you can think about the continuum as a superstructure that encapsulates any design that fall within the space. And the space is, the unification of B trees, LSM trees, B epsilon trees, and some hybrids. What design continuum does is that it breaks the superstructure into a set of fine-grained knobs. And so that if you set values to these knobs, you not only can represent a classical design, like a classical B tree or LSM tree, but you can actually capture several other hybrids within this space. Okay, let's look at an example of what I mean. Let's take the example of log-structured merge trees, which is a popular form of data structure which is used within today's key value stores. Now, LSM trees has an in-memory component, which is an in-memory buffer, and it also has an on-disk component. So what happens is when the buffer gets full, the data is flushed to disk as a sorted immutable run. And then the data keeps coming in, and when the buffer gets full again, the same thing would happen all over again, but this time, the design of the LSM tree can dictate if the flushed run would be merged with the existing runs of the level. So if it is merged greedily, then the merge policy is called a tiered leveled policy, and the tree starts looking like this. Whereas, if the runs are not merged greedily, then it's a tiered merging policy and the levels start looking like this. And as you can see, as the tree grows, data starts getting organized into levels of exponentially increasing capacities. And in addition to this, like we've said before, LSM trees also have an index layer, which consists of in-memory Bloom filters and fence pointers that allow faster lookups within the tree. Okay, so now that we know like an overview of how LSM tree works, let's review the design continuum perspective of this LSM design space. So the design continuum breaks this space into a set of knobs, and the first knob is the size ratio. The size ratio is nothing but the growth factor, which controls how large a particular level can be as opposed to the previous level. Then comes the next knob, which is the merge threshold. Merge threshold is an indicator of how greedy the merge policy can be. So if the merge threshold is 1, it's leveling. If the merge threshold is more than 1, it can be anything, it can be tiering, or it can be a hybrid between leveling and tiering. One assumption we have with the LSM design space is that there is always enough memory to hold the in-memory Bloom filters and fence pointers. But this may not always be true. Different applications, they work under different constraints. And since we are interested in the cost performance trade-off, there might as well be cases where you may not have enough budget to buy enough memory to hold all the in-memory, Bloom filters and fence pointers. So the continuum proposes that we divide the levels into 2 parts, the hot levels and the cold levels. The hot levels are the one which is closer to memory, and it has the support of the in-memory data structures. And the cold level is not close to memory. It does not have the in-memory data structures, but a way to access the cold levels is by using cascading fence pointers. Cascading fence pointers are very similar to what we are using in memory, just that it's on disk and it's embedded within the levels above. Okay, and like you've seen that the structure of the hot levels and the cold levels can be very different. So in order to have more flexibility, we divide the merge threshold separately for hot and cold levels. Okay, and then if we have, the total memory budget, we also have knobs to control how much of memory goes to the buffer or the Bloom filters or the fence pointers. And when we lay out all these design knobs, after this, as we set values to these knobs, we can make this superstructure look like a leveled LSM tree, or we can, make it look like a lazy leveled LSM tree, where we have, tiered designs at the top and a leveled design at the bottom. We can make it look like a B tree, or we can, capture any other hybrids in between. Okay. So as we set values to these knobs, you can imagine that we generate a ton of different new designs, and not all of them are necessarily great designs, right? So we should be able to have some means to prune out the bad designs or the suboptimal ones and, really pick the best design. So how do we do that? So historically, computer scientists or us, we've relied on worst case models for doing this. And so design continuum proposes worst case IO models such that if you just feed in a workload and a data structured design, you get the worst case IO cost. But for the next slides, we are going to see how worst case models are not really suitable for this cost performance analysis, and they're not appropriate to be used within cloud setup. And that brings us to our first contribution of, figuring out the sources of error in the worst case model. Okay, so for the interest of time, I'm going to focus on a single operation type here, but all our observations would generalize for any operation type. So let's begin with single result lookup. Single result lookup is that operation where the key exists in the database and we're looking for a key, for that key. To the right, what we see is the expression of single result lookup. But again, we are not going to go into the details of mathematics, but we will still see what each of the terms semantically means. So the first term is the term that comes from doing an IO on the data block that actually contains the key. The second term comes from doing additional IOs even before doing the actual IO by just going through the hot levels simply because of the Bloom filter false positives. So the Bloom filters, guide us to some level where the key does not exist because that's the false positive result of the Bloom filter, and so we need to do more IOs.
So a clarification, can you, or maybe you will do it anyway, can you explain what is the Z, the Y I think I see, but the Z parameter?
So the Z is the cold merge threshold for the cold levels.
So it's like L minus Y.
So L minus Y is the number of hot levels. Y is the number of cold levels, and Z is basically the cold merge threshold. So it's like how many tiers are there in each level for the cold levels.
Okay.
Yeah. Okay. And then, of course, as we have one term from the hot level, we also have an analogous term coming from the cold level that if the data was not found in the hot level, then we have to go all the way through the cold levels to do additional IOs, right? Okay. What's wrong about this? So there's nothing wrong about this because this is a worst case analysis. But it means that in general, for any workload, if we use this model, we can get errors. So the first error is that you can see that the cost of a single result lookup is always more than 1, which means that we do not take into account that the key may reside in memory, and so there will be no IO in the first place. So that is the first source of error. The second is that we always assume that we are going to go through all the hot levels, and so we actually go till the very last hot level. And the third source of error comes from the fact that the key won't reside, we do not take into account that the key will reside in any of the hot levels, and so we will have to go down all the way to the last cold level. So this is one extreme of a situation where we really think that in order to look up for a key, we need to go through all the levels of the tree. And as you can imagine, this is clearly a lot of overestimation that brings in inaccuracy in the cost performance trade-off. So let's look at what kind of inaccuracy we are dealing with here. So let's say, I fed in a workload and design to the worst case model, and say the worst case model.
Sorry, as a question, so this type of modeling, all the assumptions of this model was at least initially designed for the non-existing query. So I think here the fundamental idea is that if the fundamental difference is that if we expect the data to be there, the worst case model is far off the average case.
Right.
Why,
right.
if the data is not there, the worst case is the average case.
Yeah, you're right.
Okay. Okay.
Yeah. Only one thing I'm going to add here is that if you are sure about, like, if your model is such that you're sure that the data does not exist, then in that case, you can also take off the other decision that you will not probe the data structure at all. And in that case, you can, reduce the number of IOs you would do for a zero result lookup as well. Like,
right,
if you're
of course. I mean, I guess it's all about the fractions. Because if you know that nothing exists, okay, you never do anything, right? So yes, that makes sense.
Yeah, that's right. That with zero result lookups, the amount of advantage that you can gain really from by another case of average case modeling is not that much, because it's very close to the worst case model. Yeah. Okay. So so let's take this example where say the worst case model gave us an overestimation that okay, it's going to take 1,000 IOs, whereas maybe in reality it takes about 100 IOs. Okay. So if you have a performance requirement of say T IOs per second or a throughput of T, then the latencies would look like this. And because you believe in the worst case model of having this 1,000 IOs, you're going to prepare more hardware to support this with this given throughput. And so what's going to happen, this hardware would be clearly an overestimation that what you need. And so the relationship that you're trying to establish from a design to a hardware, which also in turn, like we'll see how it also affects cost, is going to be wrong. So just to give an analytical sense of how much of overestimation we are doing with the worst case. So here I'm seeing different workloads by varying the number of reads in the workload. And in general, we see that the worst case is a deviation from the actual case. But what we also see is that the worst case performs worse as the number of reads in the workload increases. And this is simply because the way the reads are modeled within worst case. So like I've said, n lookups means n IOs or even more, which is not true in the real case, right? Because there are a lot of other factors that come into play, like caching, both at the operating system level and the database level, or the fact that the distributions, like the lookups can be skewed. Like you can keep looking up for the key again and again, or you might just find the key in the first level and so on. So now that we have this problem of overestimation, so that brings us to our second contribution, where we propose the distribution-aware IO models. So the idea of these models is that we not only would capture the composition of the workload, but we also take advantage of the distribution with which the reads take place or the writes take place, or even the distribution at which the database was created in the first place. And that helps us to reason about the probabilistic existence of keys at different levels of the tree, which in turn is going to help us reduce or get the estimated IO cost closer to the actual IO cost. So we designed the distribution-aware IO models based on two key intuitions. So the first intuition is also for the intuition for read, which is called the early stopping. And the idea is that if keys are found in buffer or at higher levels of the tree, then you do not really have to bring in the lower levels of the tree into memory. And that's where you save computing additional IOs. That's not going to happen. The second intuition is the intuition for writes, which is called infrequent merging. And the idea is that if there are multiple updates that take place on keys that reside in the buffer, then that reduces the frequency at which the buffer is flushed, because within buffer, all the updates are in place. And if that reduces the frequency of flush, this in turn also controls the frequency of merges at deeper levels of the tree. Again, so today, because we are focusing on reads, I'm going to focus mainly on early stopping. So the way we model the cost of a single result lookup in this distribution aware case is that we take into account the outcome of two random variables. So the first is a random variable which controls the IO cost of reading the data from the block that actually contains the key. Ideally, this is a binary random variable because the key may or may not exist in the database. But for single result lookup, it's always 1. The value of this variable is always 1 because the key exists. The second random variable captures... Okay, sorry, I just got an echo. Sorry about that. The second random variable captures the IO cost of actually... Yeah, sure. We have a question.
So my question is that if the data is in buffer, then the lookup cost should be 0.
Yeah, you're right.
So even in case of single result lookup, it can be 0 if the data is in buffer.
Correct. What is happening here is that we will eventually take an expectation that we are going to see. So we are going to multiply the outcome of this actual variable with the probability of its occurrence. And this probability is going to come from the fact that if the data is in buffer or not. Okay, do we have more questions? Okay, good. So the second random variable comes from the fact that we may have to go on, so it captures the cost of going through the hot levels and the cold levels. And again, within each of these, we break it down into fine-grained building blocks that captures the cost of accessing a tier of a level. The way we model the building blocks is as follows. So we take into account the two sources of randomness. So the first source of randomness comes from the fact of comes from the Bloom filter false positives. And the idea is that if the probability that you are going to touch a particular tier of a level really is driven by the false positive rate of the Bloom filters. And the second source of randomness comes from the tree structure itself. So for example, the probability that I'm going to touch the third tier of the third level is conditioned on the fact that the key firstly exists in the data structure. And then the key must have been absent in the buffer and the first level and the second level. Oops, sorry. Yeah, I messed up with the animations. So the probability that the key is found in the third tier of the third level is really conditioned on the fact that it is not found in the previous levels of the tree and also the previous tiers of that particular level. And while this logic to determine the probabilistic existence of keys at different levels of the tree stays the same regardless of the distribution, what changes with the distribution is the tree structure itself. So everything starts from our estimation of the tree structure in terms of how many levels the tree can have, or say how many tiers the tree can have, and so on. And when we estimate this tree structure, we not only take into account the structural knobs which were part of the design space, like the cold merge threshold, the hot merge threshold, the size ratio, but we also take into account the distribution with which, say, the bulk writes happen in the tree, or say the distribution with which reads happen, or what is if it's uniform, what is the universe size, or if it's skew, what proportion of data is being skewed, and so on. And it is really these distribution-aware quantities that make the tree look different. And once the tree starts looking different, the building blocks start looking different. And once we figure out how the building blocks look like, now we can really take an expectation on this equation to get the closed form expression of the IO cost, which is also very close to the average case analysis for, and that changes with the distribution, right? Just to give a sense of how we are doing in comparison to worst case is that the estimated cost using the distribution aware models get way closer to the actual scenario. But again, we are going to review all of these numbers when we move to the demo to see that the distribution aware models work the best when we have some sort of skew, because for uniform.
So can you, sorry, I have a question. Can you maybe share more? I don't know if you have exactly what exactly you have in the next slides, but I think it's very interesting to share more details about what type of modeling you do for the random variables, what type of distributions you are expecting, and how you are putting all these things together, because this is very interesting, but I'm curious to actually dig deeper. I don't know if you have these slides, but yes, so the more detailed the better, I guess, for me at this point.
Okay, let me quickly see. So okay, let me see if I have the slide. I should have a slide. Yep. I think I do. Yes, let's pick this slide. Okay. Yeah, I need to just unskip it. Okay, thanks for asking this question, because this gives me an opportunity to bring this slide, which was originally chucked off.
Great.
Yeah, so the idea is that, this is an example that I'm showing with the uniform distribution, where the idea is that if you don't worry about the compaction for now, then at any level, the amount of data that you can have is really a function of what is the buffer capacity and how many flushes it took for the level to be full. Right? And if you, for example, know the size of the universe, then like for the uniform distribution, you can reason about the existence of a key in buffer by simply, whatever is the buffer capacity divided by the universe size, that becomes the probability of a key staying in the buffer. So now that you have the probability of a key staying in the buffer, then you can reason that after n number of flushes, what's the probability that the key is going to find, that the key is going to be found in the first level, and so the second level. And so what I'm showing here is that if you know the number of entries in the buffer, of course, the structure of the tree for hot level and cold level would change. But within a hot level, we can reason about the number of keys that can stay. And you can see that we can bring in the other knobs like the size ratio, the hot merge threshold, and even for the cold levels, we can bring in the other structural properties because of the cascading fence pointers. And now we can reason that what is the probability that a key is found in the particular cold level. And this is what we do for uniform distribution. For skew, just to give an overview of how it works, is that we partition the data into special keys and regular keys. So that special keys are the ones that are used more frequently with a certain proportion of, they are written more frequently, or they are updated more frequently, or they are read more frequently. And with this frequency, we can revisit all these equations separately for special keys and regular keys, and then consolidate the result for skew.
So is it important? That's great. That's great. Thank you. That actually, sheds a lot of light in my question. So is it important to have the universe size versus the data size? Because the universe size can be huge, and or maybe this is a way to capture the probability of even of whether the value exists at all.
Correct. So I think the idea is that the way we think about filling the buffer is that a buffer is filled with random draws from a universe, which is the key space. And so that's where we kind of bring in the size of the universe to figure out what is the probability that the key exists in the buffer, if you just think about the entire space of universe. Or what, and then like if we can reason about these blocks, then we can also reason about some, let me see if I can, we can reason about some more holistic probabilities. Yep. Okay. So, the last one, the second probability that you see, that if the key exists in data structure, this is particularly important for zero result lookups. If you know the key is, if the probability is really less, then you can reason that you do not have to do an IO for this at all. Okay.
Yes, thanks. That makes sense.
Yeah, and then a lot of the holistic probabilities, depend on the conditional probability, like the first one that you see. Like, what is the probability that a key exists in disk is really conditioned on the fact that the key exists in data structure, and then the numerator is that it's not in memory but on disk. And then each of these are broken down into those building blocks that we've discussed.
And this alpha comes from the buffer.
Buffer, and then all the alpha i's where the I is not equal to 0 really comes from the levels.
But this is alpha to the I or alpha I?
Alpha to the I.
To the I, okay. All right, thanks. Yeah, that actually sheds a lot of light.
Okay, thank you. Let's get, okay. Yeah, so yeah, we're going to look more into these numbers, when we get to the demo, that worst case and the distribution aware are very close when everything is super uniform. We start, there's an echo again, I think. Okay, yeah. So we start seeing the advantages when we get into skew. So more the skew, the better advantages we start getting with distribution aware models. So now that we know how designs or data structured designs really map to performance and how it is a core component of this cost performance trade-off, we move to our third objective, where we are going to see how we can bring in hardware into this pipeline given our budget. So this is the three-dimensional search space that we talked about earlier, and we were right now focusing on this particular plane. Where we were seeing how designs map to performance. What we assumed is that we had some partial knowledge about the hardware, like we knew what was the amount of memory to begin with. And with that, we somehow created the design space and applied the models to get the optimal configuration, right? Now, the position of this plane in this three-dimensional place can actually vary. So you can have it along different points in the cost axis, along the cost axis. And if the position changes, the cost value for that plane changes, which in turn, generates new hardware configurations. And if the hardware changes, you start creating more and more design space. So if we have to find out the optimal configuration from this entire space, our to-do would be to find out all the points along the cost axis that generates new hardware configurations. Okay, so we are going to see how we can generate the hardware space. So for generating the hardware space, I'm going to refer to this, where we, for every cloud provider, we have a subset of virtual machines. We take that, but we can add in more and more virtual machines. For every machine, we have its own processing power, its memory capacity, and then there's an hourly rate. Within a cloud provider, for all the instance types that we are using, we can create a vector, which we also call as the VM vector. That means that how many type of each machine we can purchase, and each of these maps to a certain cost value. Now, once we have this information for all the different cloud providers, for each of the VM vector, we take in the input workload, and we partition it proportionally across the VMs. By proportionally, I just mean, shard the workload based on the capacity of VM. I mean the memory capacity of VM. And for every VM workload combination, we can run the distribution aware model once to get the optimal designs for each of these VMs that we can use. So what happens at the end of this stage is that we have a cost, we have the complete hardware configuration, and then we have a mapping to the design vector of that hardware configuration. So what's happening is that what we've pruned in this entire process is that we've pruned all the different possibilities of designs we can have for this configuration. So now you can think that in this entire search space, I have got rid of this design axis. So I'm left with only the cost and performance axis. And at every point, I have the optimal configuration at this point, which is, the combination of that design that we've pruned out of the models, the hardware, and the cloud provider. And again, the cloud provider really comes from the hardware configuration. Okay, and once we build this continuum, now we can, so far we've just used the input workload to build this continuum. So now we can use the input budget as well to, get to the correct position of the continuum and just get the optimal configuration out of it. So now that we know, I think I've gone a little bit fast for the last phase. So I think I can explain a lot more about this using the demo. So let's move to the demo, which is our fourth step. Okay, I just stopped my sharing to move to the demo, and let me restart it again. Can you see my screen?
Yes, we can see it.
Okay, just a minute. Let me adjust what I... okay, cool. Yeah, so this is the online demo of Cosine that we have. And using this demo, we are going to see how we can feed in a workload and a budget to Cosine. And we'll review how Cosine does about, what it does about it. Okay, so this is the input interface. The input interface comprises of some mandatory inputs that we need for Cosine to work. And that comprises of the data, some information about the data, the workload, and the budget. And okay, let me start with the default, but let me still show you what this means. So I have the number of entries that I'm using. There's some default value that I'm going with. There's an entry size, key size for workload. My first example would be with uniform. We have a budget of about 3,400 set to default. By default, we consider users are cost conscious, but if we want, we can make them performance conscious as well. So it's just a priority that if the users care more about cost or more about performance. And by default, we set all the cloud providers on. But if you want, you can pick the cloud providers you like, and then it's going to work the same again. So once we have this, then okay, let me move this a bit here. So the output of Cosine can be categorized into three different categories. The first is a basic layout where we kind of compare the suggested configurations of Cosine with how things would be if we run the workload on existing systems. The second category is where Cosine helps us do interactive what-if designs. We can ask questions to Cosine, and it can quickly tell us answers about what if I change my budget, or what if I change my provider, what if I just want to increase my performance by 10% and all of those. And in the third category, we can actually get more holistic metrics about some interesting statistics that we are going to look at. So let's start with the let's start with the first. Okay, yeah. So let's start with the first phase where we are going to see or compare how things go, when we, we are going to look at the suggested configuration. The first one is that for every configuration, you see that Cosine gives you a set of hardware that you should use. For example, it suggests you what would be the number of processors, how much of memory you should use. For example, the first one uses about 16 gigs of memory. The second uses about 13. And you also get to know how much of memory should go for the buffers and Bloom filters and fence pointers. You can see what would be the data layout, like the design for the data layout. For example, for the first case, we see that Cosine is suggesting us a growth, like a size ratio of 8 with merge thresholds of 7. For the second, the growth factor has changed to 7, and it is suggesting us to use merge threshold of 6, right? The first one is an Amazon configuration. The second is a Google configuration. Now, remember that the input budget was 3,400. For the first configuration, Cosine suggests you with a budget of 2,300 roughly, and that means that anything between 2,300 to 3,400, if you spend, you're not going to get an increased performance. So that's where the optimization comes into play, that you can get the same performance at just 2,300. The second design is more for performance conscious users who do not care to add another 400 bucks, or I guess 66 bucks. Yeah. So the user can add another 66 bucks and get an improved performance of say 9.6 hours. Whereas if we, run this workload with WireTiger or Faster, okay, so again, Faster is another key value store that we have integrated here along with RocksDB and WireTiger. Faster is based on log structured hash tables. So the idea is that if you run the workload on any of these storage engines, then you would have got significantly worse performance. For example, you see that for Faster, it takes about 15 hours. For WireTiger, it takes about 22 hours. And same
So all of these are model based?
No, okay, that's a good question. So all of these are coming from the actual values, but for our own verification of the models, what we do is we kind of run Cosine configurations equivalent to RocksDB or equivalent to WireTiger, and we test it out there. So that is the verification of models that we do. And based on that, we can report the values. Like it's more about if we can trust the models. So the verification are done because of that. Does this answer the question?
Yes.
Okay.
Thank you.
Okay, okay. And then, yeah, so this is the basic interface that we have. And then we move to the interactive what if design, where we can ask Cosine questions, and then in the interactive panel, Cosine really gives us answers by changing the configurations based on our questions. And to the extreme right, what we have is the continuum that we talked about even in the slides, where it just shows that as you go from a certain cost, at every point, we really get new configurations. Like every point will have its own set of provider, hardware, design. And so each point is different from the other. So for example, if we just now ask a what if question.
So this is not a very good advertisement of Microsoft, right?
Sorry? Oh, yes. Yeah, that's a good point. So what we see here is an interesting fact that Azure generally takes away the design space with low budget. So when we have a lower budget, like you can see that right now I'm using a budget of about 3,400. Let's say how things would be for if I change my provider to Azure, and I'm going to see that the performance decreases. Let's see. Yeah, so what you will see is that we were dealing in the zone of 5 hours or 10 hours, I remember, and now it's about 18 hours. And the reason is that the throughput or the maximum IOPS that Azure provides is significantly less than that of Google or Amazon, but it can really serve workloads at budget where Amazon or Google wouldn't have been, like they cannot be used at that point. So they really they share a complementary space in this continuum.
Okay, thanks.
Yeah, right. And so yeah, we can actually ask what if questions here, and then we can, let Cosine figure out the answers very quickly. And the way Cosine is doing that is just by navigating across the continuum and exploring the neighboring points. It's not creating the continuum all over again. Okay, and then if we look at the statistical analysis, what we are seeing here, like there are a lot of statistical analysis that we can, okay, I think it's because of the interactive what if design that Azure is taking up all the space at the moment. Let's just what we're going to see is some of the interesting statistics, like who is the cloud provider that is taking up most of the design space, or say what is the IO cost that we are using. Okay. Let's say here in the first analysis, you can see that this is the analysis where we show 50% of the cloud providers, like who is there in the top 50. And you can see that GCP takes away more than half of this space by contributing to like by 25% or even more. And then the minimum is Azure. If you look at the breakup of IO cost, this is what I was trying to say, that because our workload is uniform, what you see is that the read cost is still very close to 1. I think if we just roughly zoom in, we will see that the read cost is very close to 1, which is also true for worst case models. And that's because this workload is uniform. In the next example, I'm going to try with the skew workload to see how this happens, how this changes. Other than that, we also have some interesting metrics. For example, how many designs are really classic designs and how many were hybrids. So if you just look at this, you will see that there are plenty of hybrids that are found within the continuum. So classic designs are the ones that are the default designs that we anyway choose from off-the-shelf key value stores. Okay, so let's now change the workload to skew, and let's say we pick 80% of reads are skewed. So we are going to see what kind of advantages we get out of skew. The main advantage of skew really comes from the fact that early stopping gets dominant. The fact that keys are like the keys that are looked up, the same key is looked up again and again. So it's the probability of key being found in the memory increases. And that in turn reduces the overall IO cost. We will see that. Okay, this is a skew workload. So just to start a little bit from the beginning, we see that the total time to execute the same workload has gone down because not much IOs are happening. It's a skew situation. And if I again look at the statistical analysis, I'll see that the IO cost for reads have gone down to about 0.6 as opposed to just 1 IO per lookup. And this value really changes based on the skews of reads or writes and when they also come together. Well, other than this, I think for the demo, we have a couple of other stuff going on that I don't fully have the time to cover today, but I'm still going to show what's going on. For example, there are multiple different things that affect cost and performance in cloud. And it's not just always about, picking the best design or maximizing the performance, but people do care about other stuff as well. For example, how much of services will a cloud provider have when it comes to offering periodic data migration, or how much of backup and recovery support will the provider provide? How can we count on the availability of VMs? Will it be down, say, for 50% of the time? Then it's no point, right? So all of these, what is the durability? And all of these factors do participate in our overall choice. And I'm happy to talk more about this offline. But yeah, this is again another set of argument. And so while we are close to the end of the presentation, just before wrapping up, I'm going to also quickly mention some of the ongoing work that we are also doing in this direction. So right now we just have the cost models, and the cost models do give us a sense of the estimated configuration that's going to work the best. But we still need to use that, and we need to support a self-designing key value storage engine in order to do that. So one main direction of work that we are doing right now is to make this templated storage engine, so that once we have finalized the optimal configuration, we can simply deploy it on the storage engine and start using it for that workload. And secondly, it also comes, like every decision right now is made before the workload even starts. And like applications keep changing, workloads keep changing. So we need to support the adaptability of designs so that we do not stick with the choice that we've made before even the workload started. And so that is again one of the ongoing work directions that we are doing right now. Well, thank you so much, everyone, for listening.
Can I ask something before you?
Yeah, I'm happy to take questions. Yeah, go ahead.
So you previously said that you need adaptability, but you said at the start of the presentation that maybe switching between providers or changing the architecture of the system might introduce a lot of cost.
That's true. And that's really a great observation, I would say. So let me put it this way. Adaptability would mean three different things. It might mean switching between providers, or it might mean staying with the same provider or switching between hardware, or it might also mean staying with the same hardware, but just switching the design. So it has different levels. And like you've said, I think right now our focus would be switching between designs in the same hardware or switching even within hardware with the same provider.
Rather than switching providers, I guess.
Yeah, I think switching between provider would bring in other dynamics that we will need to include in the cost models. It's not something we've thought about at the moment because, yeah, I think the focus is more on switching designs and hardware with the same provider.
Okay, thank you.
All right, let's thank the speaker. You can unmute and clap if you guys want, as we do.
Okay, thank you, everyone. It sounds good.
So I do have one question. So maybe you can say a couple of sentences about concurrency and robustness as your ongoing work to see what you are doing or what you are thinking of doing in these dimensions.
Yeah, about concurrency, I think the idea is that the cost models are going to hugely change once we start bringing in threads and once we start reasoning about how CPUs affect the cost models. The models are really IO based right now, and so we've really seen the situation like no storage engines are they use a single thread. All of the storage engines are multi-threaded. So if we really want to get this work up and running, we have to bring into picture the idea of threads and how it affects the cost models. Some of the work in this lab, like it's not related to Cosine, but some of the ongoing effort in this lab is to reason about what is the trade-off of having multiple threads, or if we just keep adding threads, what is the relationship to the overall runtime? Is it linear? Is it like what kind of relationship that is? So some ongoing work is going on in this direction about concurrency. About robustness, I guess the idea is that right now like you've seen, we are doing just a couple of designs like log structured hash tables, B trees, and LSM-tree variants. But there are other designs as well, right? Like there is cache oblivious look ahead trees, for example, or FD trees, or even in-memory data structures. So what's going to happen if we start adding these data structures? Can we really keep up using the same cost models, or can we promise performance like we are doing with the smaller design space right now? So that is also a direction of ongoing work that I'm having.
I see, that's very interesting. I guess as a thought, and this goes hand in hand with adaptability, right? If you are very sensitive and you are adapting very easily, and you have to go between different designs, that then you have to see the adaptation cost, and effectively, maybe sometimes your model would say you should go back and forth between a couple of designs, and you don't want to do that, right? So that's I think this goes hand in hand. The two, adaptability and robustness that you're mentioning, they go hand in hand.
Yeah, I agree.
Great. Okay.
I agree.
Yeah. Sorry. Go ahead.
Yeah, it also makes, I think it needs a lot of reasoning about what's coming in the future, because once a decision is made, if we have a good knowledge of what's happened, like how frequently the workload is going to change in the future, then we can reason about if the decision we are going to take now makes sense. So yeah, so it needs some sort of knowledge about the future as well, which I think wherein like a little bit of learning would come into picture as well. Yeah.
Great. Any other questions from the audience?
Yes, I have one. So, can I know that the tool you use to build your demo? Because your demo seems so nice.
Okay, I think yeah, I'm gonna have to be honest here. That the demo it does not depend a lot on fancy tools, other than the fact that we've relied on Google fonts, Google templates, and stuff that can be integrated very nicely with online setup. Other than that, it's just I would say normal cascading style sheets.
Okay. Okay.
Yeah.
Thank you.
So to add to that, this is just a lot of work.
Yeah,
Yes,
just
I can see that.
thanks.
But it's a very nice website and a very nice demo. I think it showcases very nicely what the contributions of this work are. Okay, so last call for questions from the audience. All right, let's thank our speaker again.
Thank you so much, everyone. Thanks for being here.
Let me stop recording.